Imagine AI data centers floating 400 miles above Earth, powered by the sun 24/7, processing trillions of calculations while never needing to be cooled by water or connected to a power grid. It sounds like science fiction, but Google just announced it's making this a reality by 2027. Project Suncatcher, that's what Google is calling its most ambitious moonshot yet. A plan to launch constellations of satellites carrying their custom AI chips into orbit, where they'll form data centers powered entirely by solar energy. This isn't a distant dream. Prototype satellites launch in early 2027, just over a year from now. Welcome back. I'm Christopher Wales, and today we're breaking down Google's mind-blowing plan to put AI data centers in space. Why would anyone want to do this? How would it even work? What problems could it solve? Could this actually change everything about computing, energy, and even how we tackle climate change? By the end of this video, you'll understand why space may be the future of computing, the massive engineering challenges Google needs to solve, and why this could be the biggest shift in technology infrastructure since the internet itself. Let's dive in. To understand why Google wants to put data centers in space, we need to talk about the massive energy problem facing AI development right now. AI is exploding. Every few months, models get bigger, more capable, and more power-hungry. Training a single large language model can consume as much electricity as hundreds of homes use in a year. Google, Microsoft, Amazon, and Meta are all racing to build bigger and bigger data centers to power their AI ambitions. There isn't enough energy on Earth to power the build-out they're planning. That's not hyperbole. That's what Google engineers are saying. The demand for AI data centers has grown so large that terrestrial power grids are struggling to keep up. Data centers already account for about 2% of global electricity consumption, and that number is projected to reach 8% by 2030 if current trends continue. That's creating massive problems. Electricity prices are spiking in regions with heavy data center construction. Environmental groups are criticizing tech companies for driving up carbon emissions, and residents are paying higher utility bills to subsidize big tech's AI dreams. Companies are investing in alternative technologies. Small, modular nuclear reactors, jet engines for backup power, even restarting decommissioned power plants. But these solutions take years to deploy and still rely on terrestrial resources. Google looked at this problem and asked a radical question. What if we don't try to generate more power on Earth? What if we go where unlimited clean energy already exists? Space? The sun produces more power than 100 trillion times humanity's total electricity production. In the right orbit, a solar panel can be up to 8 times more productive than on Earth. And most critically, it produces power nearly continuously, 24/7, no batteries needed. This is the insight driving Project Suncatcher. Space may be the best place to scale AI compute. So how does Google plan to actually build data centers in space? The concept is simultaneously brilliant and insanely complex. Project Suncatcher envisions compact constellations of solar-powered satellites equipped with Google's custom TPU chips, tensor processing units designed specifically for AI workloads. These satellites would fly in what's called a dawn-dusk sun-synchronous low Earth orbit at about 650 kilometers altitude. Here's why this orbit is brilliant. It keeps satellites in near-constant sunlight by following Earth's terminator, the dividing line between day and night. The satellites essentially orbit the edge of sunset, staying illuminated nearly 100% of the time. This allows them to receive up to 8 times more solar power per year than panels on Earth at mid-latitudes. But power is just the beginning. The real innovation is in how Google plans to network these satellites together. Each constellation would contain roughly 81 satellites flying in incredibly tight formation, just hundreds of meters to a few kilometers apart. That's thousands of times closer than current satellite constellations like Starlink, where satellites are separated by 120 kilometers. Why fly so close? Because Google needs to achieve data transfer rates of tens of terabytes per second between satellites to match the performance of terrestrial data centers. They plan to use free space optical links, essentially laser beams for communication. Current tests show that they can achieve about 1.6 terabytes per second, And with advanced multi-channel dense wavelength division multiplexing, they could reach the tens of terabytes needed. Think about what this means. These satellites would work together as a distributed data center, just like servers in a traditional facility. Tasks would be split across multiple satellites, processed in parallel, and results combined, all happening in orbit at speeds approaching what's possible on the ground. Google's approach is characteristically practical. Instead of building massive monolithic space stations, which some startups have proposed, they're using small, modular satellites connected wirelessly. This dramatically reduces launch costs and complexity. If one satellite fails, the constellation continues operating with redundancy. The satellites would communicate with Earth using optical downlinks to ground stations, sending results back and receiving new computational tasks. Most of the heavy computation happens in orbit, reducing the data that needs to be transmitted and taking advantage of that unlimited solar power. It's an elegant solution to an impossible problem. How do you scale AI's compute when Earth's power infrastructure can't keep up? Answer: don't scale it on Earth. Of course, nothing about putting data centers in space is easy. Google faces engineering challenges that range from difficult to seemingly impossible. Challenge 1: radiation. In space, Google's TPUs will be exposed to much higher levels of radiation than on Earth. Cosmic rays, solar radiation, high-energy particles that can damage electronics. Google took their Trillium generation TPUs to UC Davis and used a particle accelerator to irradiate the processors, simulating years of solar exposure. The good news? The chips held up quite well, suggesting they could handle a 5 or 6 year mission. The bad news? High bandwidth memory exhibited sensitivity to radiation, experiencing uncorrectable errors. For AI interference using trained models, the error rates are likely acceptable. For training, creating new models, more testing is needed to understand if radiation-induced bit flips, when binary numbers randomly reverse, would corrupt the training process. Challenge number 2: thermal management. On Earth, data centers use massive air conditioning systems and water cooling to prevent overheating. In space's vacuum, there's no air to conduct heat away. Google needs advanced thermal interface materials and heat transport mechanisms, preferably passive to maximize reliability, to move large heat loads from chips to dedicated radiator surfaces that can reject heat through radiation. Challenge number 3: formation flying. Keeping 81 satellites flying just hundreds of meters apart requires incredibly precise orbital dynamics. Google developed numerical and analytical physics models starting from the Hill-Clough-Hesse-Wiltshire equations, accounting for Earth's non-spherical gravitational field and atmospheric drag. Any tiny error compounds over time. Satellites need constant tiny thruster adjustments to maintain formation. And with space debris already a problem, flying satellites this close together dramatically increases collision risk. Google acknowledges this requires robust collision avoidance systems and ongoing debris monitoring. Challenge number 4: maintenance. When a server fails in an Earth data center, technicians replace it within hours. When a satellite TPU fails 650 kilometers above Earth, you can't exactly send a repair crew. The solution is redundant provisioning, launching extra capacity so the system continues operating despite inevitable failures. But that adds cost and complexity. Challenge number 5: launch costs. This is perhaps the most critical factor. Currently, launching anything into orbit is expensive, but Google's economic analysis shows a pathway to viability. If launch costs reach $200 per kilogram, projected for the mid-2030s with SpaceX's Starship launching at scale, then the cost of launch amortized over spacecraft lifetime could be roughly comparable to data centers' energy cost on a per kilowatt basis. That's the key number: $200 per kilogram. If launch costs hit that target, space data centers become economically competitive with Earth-based alternatives. Google isn't just theorizing about this, they're actually doing it. The company has partnered with Planet Labs, a satellite imaging company, to launch 2 prototype satellites by early 2027. These won't be full-scale data centers. They're testbeds designed to validate the core concepts in actual orbital conditions. The prototypes will assess hardware resilience. How well do TPUs actually perform in space radiation over extended periods? They'll test data transmission efficiency. Can the optical links achieve the necessary bandwidth? And they'll demonstrate sustained AI workloads powered purely by solar energy. Google CEO Sundar Pichai called it like any moonshot that will require us to solve a lot of complex engineering challenges. The 2027 mission is step 1, proving that hardware can survive and operate in the space environment. If successful, it would mark the beginning of a new era of computation, one that decouples data processing from terrestrial limits. But success isn't guaranteed. Stuff goes wrong in space. Electronics fail unexpectedly, launch vehicles explode, orbital debris creates cascading collisions. Google is taking a measured approach. Start with 2 satellites, validate core assumptions, learn from real-world performance, then decide whether to scale to operational constellations of dozens or hundreds of satellites. The 2027 timeframe is aggressive, but achievable. It's just over a year away, and Google has already tested the TPUs in simulated space conditions. Planet Labs has extensive satellite deployment experience. The mission is technically feasible with current technology, if everything goes right. If Project Suncatcher succeeds, the implications go far beyond just solving Google's power problems. This could fundamentally reshape computing, energy infrastructure, and even how we approach climate change. Implication number 1: carbon reduction. Google's analysis suggests space-based data centers could reduce carbon emissions tenfold compared to traditional facilities. That's because they'd run on continuous solar power with no fossil fuel backup, no grid electricity drawn from coal or natural gas plants, and no massive cooling infrastructure pumping heat into local environments. If AI is important enough to justify its current environmental costs, shouldn't we be pursuing the cleanest possible implementation? Space-based compute could let us develop AI without the guilt of massive carbon footprints. Implication number 2: unprecedented scale. Space literally offers more room to grow. Earth-based data centers face constraints: available land, local power capacity, water for cooling, community opposition. In orbit, those constraints disappear. Want to double your compute capacity? Launch more satellites. The scalability is theoretically unlimited. This could enable AI research at scales previously impossible. Models with trillions or quadrillions of parameters, training runs that would overwhelm terrestrial infrastructure. The next generation of AI might quite literally be beyond Earth's capacity to support. Implication number 3: new applications. Space-based compute isn't just for AI training. It could power planetary monitoring systems that process satellite imagery in real time, support autonomous spacecraft navigation for deep space missions, enable asteroid mining operations with onboard processing, provide computational infrastructure for future lunar and Mars colonies. Implication number 4: regulatory questions. Who regulates orbital data centers? What about data sovereignty when your information is processed in space? How do we prevent runaway space industrialization from creating orbital debris cascades? These aren't just technical questions. They're legal and ethical challenges that don't have clear answers yet. The boundary between Earth and the digital cloud could become more blurred than ever. Computing might become a space industry, not just a terrestrial one. Google isn't alone in looking skyward. The announcement sparked reactions from competitors and inspired similar efforts. StarCloud, a startup, recently launched carrying the NVIDIA H100 GPU, proposing to eventually build a 5-gigawatt data center across a 4-kilometer solar array in orbit. That's even more ambitious than Google's approach, betting on monolithic space stations rather than satellite constellations. But not everyone is convinced that this is practical or necessary. Some critics argue that by the time Google solves the engineering challenges and launch costs drop enough, advances in terrestrial renewable energy and nuclear power might make space-based computing unnecessary. There's also the technological risk. Data center hardware changes rapidly. Investing in satellites with a 5 to 6 year lifespan means the hardware could be obsolete before it even fails. On Earth, you can upgrade servers constantly. In orbit, you're stuck with what you launched. Environmental critics point out that rocket launches themselves produce significant emissions, hundreds of tons of CO2 per launch. The environmental benefits need to be amortized across the satellite's entire operational life to determine if there is a net gain. And then there's the simple fact that this is really hard. Space is unforgiving. Small mistakes cause catastrophic failures. Complex systems break in unexpected ways. Many moonshots fail despite brilliant engineering and unlimited funding. But we're living in highly capitalized moonshot times. The idea of building data centers with millions of AI chips on Earth would have sounded crazy a few years ago. Now it's commonplace. Perhaps orbital data centers will follow the same trajectory. Google wants to put data centers in space, powered by the sun, processing AI workloads beyond Earth's energy constraints. Project Suncatcher launches prototypes in 2027, just over a year from now. If it works, everything changes. AI development no longer limited by terrestrial power grids, computing infrastructure with minimal carbon footprint, scalability limited only by launch capacity, no electricity available. It sounds impossible, which is exactly what they said about landing rockets, reusable spacecraft, and 1,000-satellite internet constellation. Maybe in a decade, we'll look back and wonder why we ever thought data centers belonged on Earth in the first place. If this deep dive into Google's space data center plans blew your mind, hit that like button and subscribe for more content about breakthrough technologies reshaping our world. What do you think? Will Project Suncatcher succeed or fail? Let me know in the comments. Thanks for watching, and we'll see you in the next video. This is Christopher Wales for Project Aerospace signing off.